All right, no theory, only facts, right? Here's some cool music facts. Maybe you're interested in music. Maybe you're interested in music theory, but the name in and of itself is deceptive. So let's discuss some music facts, all right? Fact number one, this is a Casio SK1. Fact number two, all music is based off of one single principle, right? And we'll do as a trumpet. And this principle is that I could play, say, this and this, right? And this, right? What's happening there? Like, that's some crazy stuff. There's this interesting relationship that happens, and it's really music fact number one, right? Let's talk about music facts. The fact is that phenomenon right there, where we find kind of 3 points, play those frequencies, and those frequencies create the fundamentals of music, right? It's the idea of a doubling. So if we were to say that this frequency was a 2, and this one that we played here was a 4, and this one here was an 8, right? And this idea that this times 2, right, gives you this one, and this one times 2 gives you this one, right? It's like a string theory if you look at, and what this is called is harmonics. No fancy music terms, right? Just harmonics, right? So let's use a simple concept of harmonics, right? If we were to start with, say, a frequency like 50, right? And then and that's going to be just be called just our starting point, right? That's our frequency. And if we add 50, right, then we get 100. And so we'll say that 50 and 100, and we added 50, or 50 times 2 gave us 100, right? And then we add another 50, and we got 150. And then we add another 50, and we have 200, right? So we can say that this frequency doubled, and then this frequency doubled. So if we just ignore this one for now, right, you could say that the idea of doubling gives us this idea of harmonics, where this is now the 4th harmonic. I think this is the 1st, and this is the 2nd. Right, this 3rd we'll just ignore for now. But that's really what's happening, right? We've got this frequency, and then it doubles, and then that frequency doubles again. So that's like the fundamental of all music right there. Now the debate comes in when they go, okay, fine. We can clearly see that this doubling thing happens. Now, how long or how many steps should it take to get to the double, right? If we were to imagine it like stairs, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, let's say. Like, how many steps? If here was 440, and up here is 880, right? We know that this is times 2. Bring that up there. So we know that that's times 2. So how many steps should it take to get to your double? That's really the big debate. So over the years, let's go all the way back to, pre-1400s. It was up for debate, right? Pythagorean, I think, wanted to do it in 5 or 7. Something called equal temperament, equal temp, came along post 1400s and was like, hey, let's do it in 12, right? So this idea we could double the frequency and we're going to do it in 12 steps, right? So you go, well, that's kind of what the piano, if like we just imagine, that's what the piano's doing, right? If we do imagine, right, this is the piano, and right there is A440, right, on the 49th key of the piano, and it's going up to 880, right? There it is, right there, 440 to 880, right? So how, and it does it in 12 individual steps, right? So it's going up 12 steps to get there, right? Pythagoras thought, you know, you could do it in these proportions, right? So you look up strings and like half the string and half the string, and right? But you look at 440, you could equally, then you go cut it in half to 220, you cut that even down to 110, right? And you could keep going up, right? 880, right? With doubling, it goes, right? So here's what it looks like, you know, if you were to take the whole piano, and I use two different, what we'll call our tunings of A, right? One's 440, one's 439. But the concept here is if we look at the 49th key, we can see we're at 440, and then we kind of bounce, and we're really close, right? We're only one apart. But if you look at, you know, 220, keeps going down 110, 55, 27.5, and you can keep going up, 880, right? 1760, and this is just all the all the keys on the piano, right? So just all the keys up and up and up. So you may ask yourself, like, well, okay, so we know the facts are that music moves in these patterns of doubles, and the fact number two is something like equal temperament came along and was able to put all those into this 12 individual notes, right? And that causes us to have a scale. Now, A440 specifically goes way back, right? So if we look at just A440, we can see that a lot went on. Here are just some rough notes from a little database, starting with kind of the lowest frequency of A and kind of the date around that. The French did a huge vote in 1860 to make it 435, right? And it is international pitch. But if we look at going up, you know, you can see Bach there at 415. The solfeggios, 396 and 417, both kind of fit in the ballpark, so we could maybe look at those tunings, right? Scientific pitch, the philharmonics, the classicals. But you can see it goes from about 392 all the way up to bagpipes at like 480. And so here's some tuning forks that were found, right, over the years, right, all with these different frequencies. Beethoven, he had some of those 455. So it's really out on you know, what the frequency of A is supposed to be. If we go and look at 440 specifically, you can see this comes really out of like 1880s. I mean, you can see that there was some work on equal temperament goes way back, right? But the idea of how can we do it at the right frequency, and you can see finally at 440, the U.S. starts showing up here, and then they standardize it in 1936, and then internationally they standardize A440 in 1955 and re-vote on it in 75. And so the cool, interesting fact about another fact is the new fill harmonic. They wanted to play on this giant like pipe organ made of metal, right? And they realized when they were tuning it, it was 59 degrees. But when building would fill up with people, it would be 68 degrees. So they had to do a little math, I guess, and figure out if they tune it to 435.5, when everybody gets in the building and warms it up, they're not out of tune, right? So you can see there's definitely a desire to, right? You can see here, look at this, Sweden, Russia, Spain, they're all doing a 440. 3, the New York fill at 442, right? And there's the new fill. So when we look at, you know, so what does that get you, right? Your frequencies are just a little bit off. So what's with all this? Like, how are they calculating all of these frequencies, and what is this equal temperament? And so here's a cool thing you can print out from this interwebs. And it's basically this folded in a certain way to kind of show you how it's all calculated, right there. So 440 in this case is just the reference. You could make that anything you want, right? And it times 1 is it, right? But it times this number, 1059463, equals the next note. And that number times 1059463 equals the next note. And that times 1059463 equals, yep, the next note, and so on and so forth. If we just kind of ignore, and it's everything times 1059463, right? Every single note here to get to your octave, which is the double. This is how Equal Temperament did it, right? They used the, hidden inside here, the 12th root of 2. Go Google the 12th root of 2. Breaking 12 into 12 parts. But this is the number right here. Don't let these ones, right? You would say that 440 times 18877 equals 463.61. You see how that works? Everything's referencing the initial note, so you could put any frequency you want in here, right? And that's what I think that all these folks were after. Like equal temperament was established. But why was there this search? So here's the cool part. If you look at what Bach was doing, he was doing a 415. And if you look at the 415, that's why I put it above 440 there. It's really 440 divided by that number, because you realize you can go in both directions, right? You can go in both directions. So this is what it looks like to go, backwards from 440 down, right? And see the next one down is this 41530. And that's critical, because that's what 41530, that's what Bach was using. And so you could Google that. That's called drop E flat tuning, where you take like a guitar, right? So if you imagine Equal Temperament, here it is here's Equal Temperament on a mandolin, right? You see how the spaces are thicker here between notes. But then as you get down, I mean, they're tiny, right? And that's what Equal Temperament is. The piano really doesn't do it justice. Right, we realize that now it's just the number divided by 10, right? So it's fractal, right? 440 times this is this, this times this is this, this times this is this, and this times this is this, and this and this. So it's fractal, right? We're taking the output, we're applying the same number, and we're getting, so this doesn't do it justice. This looks like there's some sort of weird, like, maybe these keys are shorter than these, but what it looks like is this, right? This is down here. And when it gets way, way, way up here to the top, now you're looking at, realistically, probably just to here, that's kind of what this piano looks like. And so that kind of visualizes Equal Temperament. And so then you ask, well, what is the true tuning, and what does all this have to do with music theory? So then you get into the actual language of music, right? So this is where you get into the unison, which is our starting point, to our octave. Now, why do they call it an octave? Because an octave is 8. And we clearly explain that there's 12 individual steps that are equally tempered, right? Every note is the same, is the output times, right? Times 1059463. So now you get into this weird language of music where they want you to do it in 8. That's what the octave means. That's kind of the rule of music here in Equal Temperament. That's like a fact. You got to make it here in 8 to call it an octave, right? And you know it's 8 because the next one is a 7th, and then a 6th, and then a 5th, and then a 4th, and a 3rd, and a 2nd. Don't worry about the rest of the words. And then this is the 1st. 1st, 2nd, right, 3rd. It gets weird when they start calling them perfect 4ths, right? Perfect 5ths, right? These are all kind of based off of these ratios, right? How many of these fit inside of these? And if you can look at it, whether in a ratio, or you can look at it in a frequency, or you can look at it in the language of music, you can see this is kind of, you got to make it an 8. So if you just imagine we're going to start with unison, and we're going to decide to go to a major 2nd, and then a major 3rd, right? The perfect fourth, the perfect fifth, the major sixth, the major seventh, and then we go to the eighth. So you're allowed to make 8 moves to make it there. And you can see the first 2 modes here, right? Then you can go the same 8 skips to get your minors. But that just shows you that it's really every number is this times this. And so because of that, this is kind of the first concept of music. So you ask yourself, you know, what about that drop E flat? You know, if we based everything off of 4-1-5 as our A, right? Our whole guitar, everything the pattern stays the same, but this moves, right? So I hope you enjoyed some music theory.